I want to talk to you about some ionic bonding basics. Ionic bonds are formed, of course, from a transfer of electrons. One of the easiest ways to represent this is by drawing Lewis dots. So for examples of Lewis dots, remember Lewis dots are valence electrons. So magnesium has 2 valence electrons, so I'm putting 2 dots around it. I always fill my dots in. I like to start on the right, and then I fill around my quadrants moving around clockwise. So I start on the right, then I go down the bottom, then I go to the left, then I go to the top, and then I go around again until I've filled in all of my valence electrons. Magnesium has 2 valence electrons. Oxygen has 1, 2, 3, 4, and now when I'm back here again, I'm going to start forming pairs, 5 and then 6. Now, you know that the most stable electron configuration is, of course, for elements to have a noble gas electron configuration. For magnesium, that would mean losing the 2 electrons. For oxygen, it means gaining 2 electrons. So if magnesium loses 2 electrons, those electrons can transfer to the oxygen, so the oxygen can gain 2 electrons. When you have this electron transfer occur, magnesium has a positive 2 charge, oxygen has a negative 2 charge, and of course the charges balance each other out, so the formula is MgO. When you deal with elements, say I have sodium, and say I have oxygen again, when you're dealing with the charges not balancing each other out, where sodium's more apt to lose 1 electron to look like a noble gas, and oxygen's apt to gain 2 electrons, you end up with charges that don't fully balance out, like Na plus and O2 minus. You learned back in the day to do the crisscross rule, Na2, and then of course the 1 comes down here, but we don't write the 1, so we just leave it as O. That's one way to figure out the empirical formula for these ions bonding together. Now let's talk a little bit more about the energies involved in these ions bonding together. You should remember from Chapter 7 about ionization energy. It actually takes energy for sodium to lose an electron. This process is an endothermic process. Now, chlorine, if I'm bonding sodium with chlorine, chlorine needs to gain an electron. Now, chlorine gaining an electron is actually an exothermic process. So energy is actually released when this process forms. Now, here's the interesting thing about this. We know that sodium and chlorine bond in a 1-to-1 ratio. We know that eventually our compound is going to look like NaCl. The sodium loses the electron, and the chlorine gains the electron. Well, what's really fascinating about this, I'm going to write this in red here, is that the chlorine releases about 349 kilojoules per mole. For sodium to lose an electron, it requires 496 kilojoules per mole. Okay, now here's the interesting thing about this. If this is how much is needed, and this is how much is released in this process, 496 minus 349, what you end up with is you still need an additional 147 kilojoules per mole to get sodium to bond with chlorine. Now, that's funny because when you actually react solid sodium metal with chlorine gas, it's a very exothermic process. But when you look at these two values, it looks like it's an endothermic process because you're losing, hence why I have this as negative 349 kilojoules per mole, and it takes 496 kilojoules per mole for sodium to lose an electron. This is strange. So what accounts for the reaction between sodium and chlorine to produce sodium chloride for being so exothermic? Well, the answer is lattice energy. And there's only 2 things you really need to know about lattice energy. Lattice energy is what makes these types of reactions very exothermic. Energy is actually released when the lattice structure for the sodium and the chlorine ions coming together is formed. So, what is lattice energy? How can it be calculated? Well, lattice energy has the following formula. It's got a constant times Q1 times Q2 over D, which is really, you can think of that as both of the radii for both of the elements that are bonding together. So what is it that matters? Charge matters. Distance matters. Oops, I completely spelled distance wrong. It's distance, not disdain. All right, so the smaller your distance, smaller the distance, the higher your lattice energy is going to be. the greater the charge difference, the greater your energy is going to be. So there's a direct relationship between this. So if I had sodium and chlorine coming together versus magnesium and oxygen coming together, sodium and chlorine, the charge difference, they're both +1 and -1. And for magnesium and oxygen, they're both positive. One's +2 and the other one's -2. This one's going to have a greater lattice energy than sodium chloride, which means when these two ions come together to form their lattice structure, they're going to release a lot more energy. And that's why it's favorable for these two to come together. And we've observed the exothermic reaction between these two when we actually ignite magnesium metal and let it react with oxygen. Another comparison would of course be the distance. The smaller the distance between the ions, that when it forms its structure, the greater the energy. It's an inverse relationship between distance and energy, and it's a direct relationship between the charges and the energy. That's about it. That's about all you need to know in terms of ionic bond basics from Chapter 8.